Hey guys, welcome back. We're going to be continuing our study of linear regression by looking at the relationship between the height and the weight of these of several AP statistics students. So here we have our students, and here we have our lovely data. So if we look at the data, it's sorted into two different groups. We have the male data for height and weight and the female data for height and weight. So the reason we separate these two is if we didn't, they would be a bimodal distribution. We want to create two separate models for males and for females because they're going to have different slopes and different y-intercepts and stuff like that. If we put it together, it just wouldn't work out as well. So what we want to do is we want to put all of our data into the calculator. So if you get out your calculator, we're going to go to Stat and Edit, and I'm going to put all this data in. So beyond list 1 through list 6, if you arrow past list 6, you'll get something that looks like this, okay, which is an undefined list. And if we just hit enter, we can name it, and then you can name it whatever you want. So I named my first one. So we're going to go to alpha and then M. We see the little green M above the division sign. So MH for male height. So alpha H, male height. Then you hit enter. And if we arrow over again, it'll give it to you. It'll give you another list, and then you can create that one. Call it male weight, so MW, and then female height, and then female weight as well. So these should be your 4 lists, and you can put all that data in there. We can also see the amount that we have. Let me clear that out. Anyway, we can see the list size that we have here. For some reason, it redid those for me. So anyway, the male weight is going to go with the male height, and the female height is going to go with the female weight there. So next thing we want to do is actually graph it out, because if we look at this data here, it's actually hard to tell anything. You might look for something that sticks out. I don't know, 200 pounds. That looks unusual. And then over here, 61 inches, that's pretty short, but there's another 61, so I guess it's not that unusual. 88 pounds, 91 pounds, those look really light. Ooh, 57 inches. Yeah, that's really tall for a female. Also 170 pounds. But it's kind of hard to tell just looking at data. So the best thing we can do is actually graph it out. So here are the summary stats and the histograms for each variable. So this is the male height, male weight, female weight. Notice that the weights are more likely to be skewed to the right. It looks like this height was skewed. Also, that 75-inch female is probably going to be an outlier. There's also, this is not actually technically a gap because it doesn't separate two groups of data. It just means that we didn't have any females that were between these heights or between these weights. But then again, if we increase our sample size, we probably would have been able to fill in those bin sizes there. Anyway, then the mean and the median, you can tell whether or not the data is skewed by comparing the mean and median. So for instance, for the male weights here, because the mean is larger than the median, that means the data is skewed to the right, because the skewedness is going to pull the mean towards the tail. All right, so what we actually want to do is look at the scatter plots. So I'm going to graph out some scatter plots here. So go to second y equals, and I'm going to turn on, actually I'm going to turn all the plots off real quick and hit enter, done. Okay, then turn on plot 1. Scatter plot, I want to do the X list for the male height and the Y list for the male weight. So we want to know which one's the explanatory variable. So we're going to look and see how does the weight increase or change as the male height changes. So we're saying that the male height is explaining the weight, not the other way around. So anyway, I like to use the plus signs because they're precise, and then I'm going to use blue for the boys. So then we're going to do zoom 9. And oops, I've got some models here that you're not supposed to know about. So let me turn those models off so you don't see them graphed out. Anyway, then hit graph. All right, so that's going to be our scatter plot, so you can graph that out. I think this one's actually, yeah, it's okay. Anyway, and then the same thing for the females. So we're going to go to zoom 9. I think I've actually got them already ready to go in plot 2. Yeah, so female height, female weight, I'm going to use the pink color for the females. Zoom 9, so that's going to be the scatter plot for the females. Okay, so if we look at these, describe the form, which is the direction, strength, if there's any outliers or anything like that. So both of them look to be, they're both positive, so as they get taller, they weigh more. In general, they are both linear. This one looks like it might be curved, but also this outlier can be changing that quite a bit as well. The strength, it looks like the female has a stronger association than the male, so we would expect to have a stronger correlation coefficient as well. All right, now let's calculate linear regression for each gender. So back in the calculator, to do the linear regression, we go to stat stat calculate linear regression, the fourth option here. And then I'm going to do the X list is the male height and the Y list would be male weight. So second stat, and then the male weight is going to be the last one there. And then I'm going to store the regression equation for the males as list 1. So variables, y variables, function y1, and then hit enter and calculate. And so it's going to store this regression equation in for y1. So if you go to y1, that's going to be this equation here. And it'll turn it on automatically. If I hit graph, it'll graph it. But notice this is graphing the male equation with the female scatter plot. So to change that, I would actually turn on plot 1, turn off plot 2, because that's the women, and then hit zoom 9 again, and that's going to redo it. And so that's going to be the scatter plot for the males, which looks good. Okay, so let me quit out of this, and so second mode to quit. That's not what I meant to do. Second mode, there we go. And then I wanted to run that linear regression again. All right, so in that we have our correlation between the height and weight for the males, which is going to be there. The slope, if we look here, that's going to be the A, the one with the variable, which is going to be 7.2999. And then the B is the y-intercept, which is going to be that negative value right there. All right, and then for the females, we're going to do the exact same thing. So stat, arrow over to calculate, linear regression. This time I'm going to do female height and female weight. So second list 8, and then second list 9, I think, if I remember right. We store the regression for the women under variables, y variables, function y2. Okay, then to calculate, this is going to graph out the value for the women, and I can show you that. We turn off plot 1, turn on plot 2. Oops, my fingers did that again. Okay, so turn on the plot for the women, and then go to y equals, and I'm going to turn off the model for the men. Actually, I'll turn them both on, then you can see what happens. Anyway, zoom 9. All right, so as you can see here, this is why we don't want to use the model for the men, for the women, because it clearly is different, and it doesn't match the data very well because it's not made from that data. Okay, so anyway, kind of cool. So go back to the linear regression here. So I ran the linear regression for the women. It doesn't like that. I'm going to go to... Oh, it doesn't like the decimal at the end. Okay. Anyway, so the regression for the women is going to be 0.738. The slope was given there, and then the y-intercept is there as well. So from that, we can actually form two regression models. So the predicted male height, that's got the hat over the top. So the predicted male weight, excuse me, is equal to the slope times the height, then subtracting the y-intercept. Then the predicted weight for females is going to be their slope times their height minus their y-intercept as well. So anyway, those are our two models. All right, so what would you predict about the weight of someone of average height? So anytime we have someone of average height, we would always predict that they have also average weight. So that's going to be the mean point whenever we have the x average is going to go with the y average always, regardless of what the correlation coefficient is. So it'll always go through the mean point. Here I actually graphed out the standardized stat plot for the men. So when we do that, I actually kind of stretch it out vertically because we have the same x and y axes of z-scores. Excuse me, correlation coefficient is 0.752. That's actually going to be the slope of the line of best fit for the standardized plot, which is kind of cool. So then from that, we get the next question. Says if a male is 2 standard deviations above average in height. So if we go over 2 standard deviations in height, how many standard deviations can we go up? So we can't go up 2 standard deviations in weight. It's going to be the correlation coefficient times that. That's our slope, right? And that's basically the regression to the mean. So our regression to the mean equation is going to be the predicted y or z score for the y value is going to be equal to the correlation coefficient times the z score for the x value. Well, if they said 2 standard deviations above average, that'll be a positive 2. So it's going to be our correlation coefficient times 2, which is going to give us basically 1.504. So if I graph that out, if we had an x variable of 2, and then the correlation coefficient times that would mean that we could not, we basically start out at 0, and how far can we go over? Well, we can only go over the correlation coefficient times that value, which is going to be about 1.5 standard deviations above the mean for the predicted height or the predicted weight for that male. All right, what would you predict about the weight of a female one standard deviation below average? So here's the standardized plot for the females. There's their correlation coefficient, which is the slope of the regression line. It's still positive in this case. Now, if we had a negative z-score, so the x variable, so their height, the female height is one standard deviation below the mean. We start out with our prediction at the mean, the average weight, but we're allowed to pull it over the correlation coefficient times that value, which is going to be the negative 0.738 there, which would be that value right there. And that's basically illustrating the regression towards the mean, because we're always going to be pulling our estimates back towards the mean, because the mean is the most likely outcome that we're going to get. So we can only pull away from the mean with the strength of the correlation coefficient, which will always be less than 1, the magnitude of 1. So therefore we can only basically, we know we can only go so far. We can only have so much confidence to pull away from the mean, which would be less than 1. It'll never be more than 1. All right, calculate the coefficient of determination, which is the r squared, and then interpret it in the context of each relationship. So if this is a correlation coefficient that we have here, the r squared would be that squared, which is going to be, that's not going to work. Okay, so 56.6 or 0.556. And then for the females, same thing. Again, that was not going to work for me. Going over there. So what does this mean? Well, it tells us that that 56.06% of the variation in the weight in the males can be accounted for by, that is not right, accounted for by the variation in the height. So that's telling us how much variation we can remove by using the model to predict what their weight would be based on their height. Okay, write the equation for the least squares or the line of best fit for each gender. So we store these as the y1 and the y2. So basically that's what I've already showed you before. So that's the prediction for the height and the prediction for the weights. Basically, no, sorry, this is the prediction for the weights based on the heights. And then for the females, we have that right there. Sketch the residual plots. So every time we run a linear regression, it'll always form a residual form the residual plots for us. So the last one I ran was for the females. So if I want to find the residual plot for that, I'm going to turn off this one, go to plot 3. So I'm going to graph a scatter plot. My X list here is going to be the female height, so second stat, which is the female height, okay? And then the Y list is going to be the residual plot, because that's the last one that I just did, so residual plot. And then I'm going to do it, I guess I'll do it in magenta, okay? And then zoom 9, yeah, it's going to grab my models. It's kind of annoying. Let me turn the models off real quick. Why is it skipping over that one? All right, anyway. Then I'll hit zoom 9 again. Oh, I never turned that, I never turned it on. Okay, so for, there we go. How about now? Okay, so that's going to be the residual plot for the females. And then to get the residual plot for the males, first we have to run a linear regression for the males. So let me quit out of this. Again, that's not what I was trying to do. All right, so the linear regression for the males is going to be right here. Okay, cool. All right, now that I've done that, I can actually just do this again. The residual plot is going to be updated to now the residual for the males, but I do need to change the X list to the male height. So that's going to be, wrong one, sorry, stat list, and then male height, which was the 0 option. Okay, cool. Then I'm going to change the color because we are dealing with the males now. So to blue. And then zoom 9. Okay, cool. So that's going to be the scatter plot of the residuals for the males. Now, we are looking for no pattern. So again, this is random spread. This kind of looks like, again, we can see that curvature here. So we might need to straighten this out, but it's also based on the fact that we have this outlier. If we remove that outlier, that really big girl, then we probably would actually have a better model for the women, and it would probably decrease the increase the correlation coefficient for us and decrease the slope but it would actually increase that value as well. But anyway, so overall we look good with the men. We might have some issues with the female model, which we've already stated because of the possible outlier and the fact that it looks like it might be curved because of that outlier. It's kind of pulling the slope higher than it probably should be. A big difference to note is that how much different the slope is for men and for women. So for every additional inch that one of these guys are, they're going to be 7.29, basically 7.3 pounds heavier. But for women, they're less than half that. Yeah, less than half that for every additional inch, which is really interesting. Or explain what the slope of each line means in context. That's basically the same thing. So for every inch of height on average is what the model is doing. The male weight increased by 7.2999 pounds. And you can say the same thing for the females. So for every inch of height on average, the female weight increased by that many pounds. All right, so now we want to use our models to predict the weight of a 60-inch male. So to do that, we get to our models, we go into the variables, y variables, function, y1. So this will be for the males, and then use the open parentheses to evaluate it. And we're going to evaluate for a 60-inch male, which will tell us that we would expect them to be 73.59 pounds. Now that seems really light. The reason for that is in our data, if we go back to our data, we did not have any males that were only 60 inches. All of them were taller than 60 inches. So that would be extrapolation, because we're talking about a value that is not within our data set. So it's not really appropriate for us to calculate what this value is. So, I mean, we can still calculate it, but we shouldn't trust it if we're going to extrapolate like we are here. What about a 70-inch male? Now that's within our domain, so that's okay. We can do that one, and that would be about 146 pounds, so that's pretty good. And then for the females, we stored that equation for y2. So I'm going to go to second, actually just go to variables. So variables, y variables, function, second option, and then open the parentheses to evaluate it for 60 inches. Now this is technically below, the 61 inches was the shortest female that we had in our data set, but this one isn't that far off of it, so it's probably fairly accurate. But again, you shouldn't extrapolate, only interpolate. So 103. Okay, and then 70-inch female, that was pretty tall, but we did have a 74-inch or 75 foot, so 75-inch, so we should be fine, which is going to be 139. So notice 60-inch male is actually from our model is going to be lighter than a 60-inch female, but again, that's because it's such a far extrapolation and it had such a steep slope for the men and not for the women. And then also that one's not really that surprising. All right, next one, predict the weight of the following. Comment on these results. So we want to do a 68-inch, which is 7'2" male. So I'm going to go to one of the Y1s and then change this to 86 inches. And that would be really heavy. So it'd be really heavy, but the problem here, so the reason why I wanted you to comment about it is because this is extrapolation, right? We did not have any males that were this tall, 7'2", right? And so our model really isn't made for those taller males unless we were able to include them in our data set, or if we only looked at the taller males or stuff, we might see that our model kind of breaks down once we get so tall. We probably have to look at just basketball players or something like that to be able to get that to work better. So anyway, we necessarily shouldn't trust this because it's beyond the domain of our data set for the males. And for the females, if we had a 20-inch newborn baby girl, yes, technically she's female. Yes, technically we know her height, but the length of a baby, we don't even call it really their height, but their length rather, was not a part of our data set, so this would be extrapolation as well. If we evaluate it, I mean, there's nothing stopping us from putting it into our model, but I mean, it's just, you know, bad data in, bad data out. Okay, so we would say that she's negative 43 pounds. That's not even possible, right? The reason we're having issues on both of these that we shouldn't trust the values because they're extrapolations well beyond the domain of our data sets. So that's it for today. Pretty well went through the entire thing together, just making sure that you guys understand all the ins and outs of what's going on with linear regression. So we'll do another review for the next few days, and then a quiz is coming up fairly soon. So I'll see you guys later.